So
This meeting is being recorded.
first of all, thank you for the opportunity of being here. I am from Corvinus University of Budapest. I finished my PhD studies almost 2 years ago at Budapest University of Technology and Economics, and my co-author is Zsolt Darvai from Babes-Bolyai University of Cluj-Napoca. I also finished my master's studies there at Babes-Bolyai University in Romania. And today I will speak about an interior point algorithm for solving horizontal linear complementarity problems over Cartesian product of symmetric cones. So here is the outline of my presentation. In the first part, I will present the theory of Euclidean Jordan algebras and symmetric cones, just a short introductory part. And I will present this horizontal linear complementarity problem over Cartesian product of symmetric cones. And after that, I will present the so-called algebraic equivalent transformation technique, which is a method for determining search directions in case of interior point algorithms. This was introduced by Zsolt Darvai, and I will show its extension to this more general framework. Of course, I will try to make to present also other ways to determine search directions and to present their connections to each other. And in the second part of the presentation, I will present the algorithm. This is about the predictor corrector interior point algorithm. I will also show the main steps of the complexity analysis of this algorithm. And of course, there are several further research topics, and I'm going to talk about this as well. So why did we start to deal with linear complementarity problems? So we know that they have a wide variety of applications in different fields. So we know that matrix B-matrix games can be traced back to LCPs, or for instance, the Aro-Debrov market equilibrium problem with linear and Leontief utility function can be also formulated as LCPs. So quadratic optimization, so KKT conditions of different optimization problems also lead to LCPs. And recently it has been turned out that, for instance, testing compositivity of matrices can be also done by using linear complementarity problems. And we also know that the optimality conditions of several important optimization problems can be written in the form of these horizontal linear complementarity problems over Cartesian product of symmetric cones. So here we can see some papers on this topic. So Assadi et al. Proposed interior point algorithm for solving this type of problems. In 2020, we also provided a full step feasible interior point algorithm for solving this. But today's presentation will be based on this technical report, which is under revision now. And it is the extension of our previous result, which was published in Science Journal on Optimization. So this was about the predictor corrector algorithm, but only for P-star K-PA linear complementarity problem. So this is its extension to this more general framework. But I would like to mention also the previous results. So we also know about linear complementarity problems, so without this horizontal part, so linear complementarity problems over Cartesian product of symmetric cones. So Lesche and his co-authors also dealt with these problems classes. I mentioned that I would speak about the theory of Euclidean Jordan algebra. So why do we need this? So Jordan algebra were created to illuminate quantum mechanical observables, but it turned out that they have a strong relationship to other areas of mathematics as well. And for instance, we know about its connection to symmetric cones, because any symmetric cone can be realized as a cone of squares of some Euclidean Jordan algebra. And this means that Euclidean Jordan algebras provide us a very efficient tool for analyzing optimization problems, including symmetric cones. So we will see that we will use several times this approach by using eigenvalues and so-called Jordan frames as well. So here is the definition of Euclidean Jordan algebra. So let V be an n-dimensional vector space over R, and let us consider this bilinear map. Then V is called Jordan algebra if and only if for all x and y from V we have the commutative property, and the second one, which is called the Jordan identity. And the Jordan algebra is said to be Euclidean if there exists an associative inner product. And throughout this presentation, I will assume that, so I will speak about Euclidean Jordan algebra. So when we see V, I'm speaking about it. And let L be the following linear operator, which acts in this form. Of course, in special case, we can see this. And by using this L operator, we can introduce the so-called quadratic representation of V, which is given in this way, and Lx can be interpreted as this. And the degree of an x is the smallest integer for which this is linearly dependent for all x from y, so V. So I put here a small example. If it is the r to the power of 3, then this will be the component-wise product or Adam's product. And if we take, for instance, these 3 elements, then the degree of V1 is 1, the degree of V2 is 2, and the degree of V3 is 3. And of course, the rank of V will be the largest degree for all x from V4. So in this case, it will be 3. And I mentioned the Jordan frame, so this will be very important in this theory. So we say that C1 and CR is a Jordan frame if each one is a primitive idempotent, and which means that it's non-zero and cannot be written as the sum of other two idempotent elements. And if the orthogonality is satisfied, and this condition as well. So for instance, if we think on the special case when V is r to the power of n, then the canonical basis is Jordan frame, the Jordan frame. And the spectral decomposition theorem says that if we have an element from V, then there exists a Jordan frame and real numbers lambda I, such that x can be written in this form. So, and this lambda I are the eigenvalues of x, and ci are the elements of this Jordan frame. This will be very important from our point of view, because this enables us to extend any real valued univariate function to elements of Jordan algebras by using the eigenvalues and the Jordan frame. So if we assume that phi is a real valued univariate function which has these nice properties, this is just technically, so we will see later why do we need this psi square. Then if we consider an x from V, then we define phi in this way. So by using the eigenvalues and the Jordan frame, and similarly the phi prime in this way. And this will be used in our approach when we determine the search directions in case of interior point algorithms. Now, let us introduce this by using the trace where X and S are elements of V, and the Frobenius norm, which is induced by the trace inner product, is given here. Of course, it can be given by using the eigenvalues as well. And we arrived to the symmetric cone. So if we have a convex cone, then we know the dual of it. And if the cone is equal to its dual, then we are talking about self-dual cone. And if we consider this automorphism group, which contains those G from GLV, where GLV is the set of invertible linear maps, G from V to itself, then we say that the convex cone K is homogeneous if for all X and Y from the interior of K, there exists a G for which Gx equals Y. And we call a convex cone symmetric cone if it's self-dual and homogeneous. And I also mentioned that any symmetric cone can be written as the cone of squares of Euclidean Jordan algebra. So we introduce this cone, the cone of squares, in this form, and it can be so it was proven that this cone is a symmetric cone. And we will use the following notations when we deal with the complementarity problem and the optimization problems as well. So this means that X is in K, and this means that X is in the interior of K. The Nesterov scaling will also play important role in the determination of the search directions in case of the algorithm. So we know that, for instance, in case of semi-definite programming, we need symmetrization techniques, and in this case, we will deal with Nesterov scaling. So let X as being from the interior of K, then there exists a unit W from the interior of K such that X is equal to this, where this is that quadratic representation of V what was given here at the beginning of the presentation by using this linear operator L. So, and W is called the scaling point of X and S, and it can be given these two ways. Here we can see the symmetric cone optimization problem, and after that I will turn to the linear complementarity problem over Cartesian product of symmetric cones. But before, let us consider this primal dual pair. So in the primal problem, we minimize this under subject to these constraints. So X is in K. And this AX equals B should be interpreted in the following way. So if AI is element of V, then we take the inner product of AIX, and this gives us a BI. So B is an m-dimensional column vector. And in the dual problem, we maximize B transpose Y subject to these constraints. And of course, because we are talking about symmetric cones, so here S is in K. In the following table, we can see the some specific cases. So if V is R to the power of N and the cone is the non-negative order, then of course we get back the linear programming problem. And if we take the Lorentz or ice cream cone and V is R to the power of N plus 1, and taking this inner product, then we get back the second order cone programming problem. And if we consider the set of symmetric matrices with the cone of positive semi-definite matrices, then we get back the semi-definite optimization problem, and probably so this bullet is also frequently used in case of semi-definite programming problems. So these are special cases of symmetric cone optimization. And now I would turn to the more general framework. So if we consider this V, which is the Cartesian product space with its cone of squares K, so each VI is a Euclidean or Jordan algebra, and each KI is the corresponding cone of squares. of Vi. Then for any X and S, this will be the following. So we define this in this way, and in our product given in this way. And for any element from this Cartesian product space where I is element of Euclidean Jordan algebra Vi, we can define the trace and the minimal and maximal eigenvalues of the element C in the following form. Okay, and similarly, the Frobenius norm is defined in this way, where the xi are elements of the Euclidean Jordan algebras Vi. And here we can also consider the Lyapunov transformation, the quadratic representation of X, so this L and P, by taking this where Xi are elements of the corresponding Euclidean Jordan algebras Vi, and this L and P have been presented and defined previously. And in the horizontal linear complementarity problem defined over the Cartesian product of symmetric cones, we want to find a pair such that these conditions are satisfied, where Q and R are linear operators from V to V, where we are talking about the Cartesian product space V. Q is element of V, and K is the symmetric cone of squares of the Cartesian product space V. So X and S are in this cone. And then the set of feasible solution of this can be of HLCP can be written in this form. So it contains those XS pairs for which the stability conditions are satisfied. Here we can see parallelism between the Cartesian SC HLCP and the standard HLCP. So if V is R to the power of N, and we are talking about the non-negative orton, then we get back exactly the HLCP. And if we take, so here we would have X transpose S, but because of the non-negativity of X and S, this will be equivalent to XS being equal to 0, so to this component-wise product. And if we put, so if we substitute here, instead of R the identity matrix, then we get back the standard LCP as well. And the LCPs are usually belong to the class of NP complete problems. However, it has been proven that if we assume that if we speak about just LCPs, not about this more general framework, but it has been proven that if we assume that the matrix, the problems matrix has the so-called P star kappa property, or if in this more general framework, if this QR pair has the P star kappa property, then interior point algorithms can solve these problems in polynomial time, of course, in the size of the problem, and then in this special parameter kappa. So that is why it is important to deal with this class. So we will deal with P star kappa as horizontal linear complementarity problems over Cartesian product of symmetric cones. And we say that the pair QR possesses the P star kappa property if for all X and S. This implies the following. So I plus contains those indices for which this inner product is strictly positive, and I minus contains those I for which this is negative. And we can see somehow positive weight here in case of those indices that are in this I plus. So if we want to think to the more specific case, so when B is R to the power of N, and if we also substitute here instead of R the identity map, then this will reduce to the standard definition of P star kappa matrices that were given by Kojima et al. And we can also see that if we substitute here instead of kappa 0, then in the specific case we would get back the semi-definite, the class of semi-definite matrices. So in the specific case, this would be a generalization of it. The interior point condition follow the so-called central path. So we suppose that the interior point condition holds in this case, which means that there exists an x0 s0 which satisfy these constraints. So x0 and s0 are in the interior of case. So this is the notation for it. And then the central path can be the central path system can be characterized in the following form. So instead of 0 here, we put mu times c, where mu is positive. And the subclass of Monteiro-Zhang family of search directions is characterized by the following. So it contains those U where U is invertible, and these three holes where L and P are the Lyapunov and quadratic representations that I defined previously. And here we have an important lemma. So if we have a U from the interior of K, then these two are equivalent, where this P is the quadratic representation of V. So if we consider a U from this subclass of Monteiro-Zhang family of search directions, and if we use these notations Q tilde and R tilde, then by using this lemma, then we can rewrite the previous, so the second system, in this form. And it has been proven that if the interior point condition holds, then the system has unique solution for each positive mu. Now, here it's also important to have that this thing that QR possesses the P star kappa properties. So for instance, if we think on just P star kappa LCPs, then if the problem matrix does not satisfy this P star kappa property, then we can have, for instance, multiple central paths or no central paths. So this is also important in this case. And I arrived to the this method of algebraic equivalent transformation technique, what I mentioned at the beginning of the presentation. So this is a technique for determining search directions in case of interior point algorithms. It was introduced by Zsolt for linear programming. And now I would like to present this extension to this general framework. So if we consider a function phi in that framework, what I have shown at the beginning by using the eigenvalues and the Jordan frame, which is induced by the real valued univariate function phi defined on psi square infinity. So here we can see why did we need that psi square at the beginning of the presentation. This psi should be between 0 and 1 with these properties, and we will assume that the smallest eigenvalues of this is larger than psi squared. This is technical. It's due to the fact to the specific search direction that we will use in our algorithm. I will show it later a little bit. And by using this approach and this function, we can rewrite the previous system in the following way. So we divide here by mu, and after that we apply the function phi. But of course, thinking on that your eigenvalues and Jordan frame. And we arrive to this system 5. And of course, for the strictly feasible x from and s from the interior of K, we want to find the search directions delta x, delta s that satisfy these constraints. Now, in the right-hand side, we have this element a phi, where we can see that this is depending on the function phi. So by having different functions phi, we will get different search directions that will lead to different algorithms. And here I summarized the search, so the functions used in the literature in this AET technique. So the identity map actually appears in almost, so in many interior point algorithms, because this would correspond to the case when we perform no transformation here. So most of the interior point algorithms use this, even if they do not call it AT approach. Okay, so and in this case, the corresponding right-hand side is this one. The square root function was proposed by Joaquin when he proposed this technique for linear programming problems, and after that they so it was used also and extended to other types of problems and algorithms as well. We dealt with the t minus square root of t together at the beginning for linear programming problems, and after that we also considered other versions and extensions of this algorithm, but I marked it with red because this presentation is also, so this algorithm presented here is also based on this search direction obtained by using this function. So in this case, we get this right-hand side, and we also have this function proposed by Kaifman and Hagidi, and we get then this right-hand side. Now, it is a very interesting question, and that how could we define a whole class of functions for which we can define interior point algorithms, and for which we can also perform and to obtain the complexity bounds and the well-definedness. So together with our research group, we are working on this, and we have several results related to this for different types of algorithms, so for long step algorithms and for primordial short step algorithms. So so this is in progress, and I mentioned that we use the Nesterov-Tott scaling scheme. So for this, let U be W to the power of -1/2, where W is the Nesterov-Tott scaling point of X, and that's what I showed in the first part of the presentation. And let us introduce the following notation. So those who dealt with more specific problems, this would correspond to the variance vector, for instance, in case of linear programming, to xs square root xs over mu. So this is the corresponding scaled search direction dx and ds computed by using this delta x and delta s search directions, and by using that quadratic representation of v. And by using all these notations, we get the following system, and this. So the right-hand side here is also depending on the function phi, but so it can be proven that this system has a unique solution. So from here we can determine the search direction. So actually that is why we needed this symmetrization scaling technique, because from here we could not, so from here we cannot determine the system does not have unique solution, so we do not know about that, but this for this we can prove that it has unique solution. We also need a proximity measure to the central path. So usually we measure the distance from the central path by using these proximity measures. In this case, we will use the following. So we take the Frobenius norm of PV over 2. And I also talked about other ways to determine search direction. So there are several algorithms that use, for instance, kernel or barrier based approaches, or Pengetol introduced the self-regular functions, and they dealt with long step interior point algorithms. There was defined this general class of eligible kernel functions, and the idea is here that we can make an association between the AT functions and the kernel functions. So if we consider this general barrier function in this form, where these are the eigenvalues, and this small psi is the corresponding kernel function, then the right-hand side of, so the second equation of the scaled system can be also replaced by this one, where this is the notation, what we can see here. So this is an element of, so if we have D as an open set and an F from D to R, then, and the big F from U to R, defined in this way by using the eigenvalues. And if we consider X given in this way, then if F is differentiable in D, then the big F is also differentiable in U, and we can use this notation. So the right-hand side here can be replaced by this one, and then we can see that we can associate to the kernel functions to several AET functions phi by using this. And in our case, when we use the function t minus square root of t, then we obtain the following kernel, kernel function, but it's not the usual kernel function in the sense that so kernel functions are convex in they have so if psi 1 equals 0, they tend to infinity as t tends to infinity, but they usually had vertical asymptote in 0, so they were defined on the whole zero interval, zero infinity interval. But we can see that in this case we do not get the usual kernel function in the sense that it is not even defined on the neighborhood of the origin. So we, together with Zsolt, we introduced the notion of psi asymptotic and so-called and the positive asymptotic kernel function, and we can see that the kernel function belonging to this AET function is a positive asymptotic kernel function. So here we can see its definition. So if we have an open interval, then a function is called psi asymptotic kernel function if it is twice continuously differentiable. This condition is the same as in case of usual kernel function, but here instead of 0, here we have a psi. And of course, a function is positive asymptotic kernel function if and only if it is psi asymptotic, and psi is between 0 and 1 strictly, because if the psi is 0, then we obtain back the usual definition of kernel function. I would like to start to present the algorithm. So predictor corrector algorithms are usually efficient in practice. So they perform in a main iteration a predictor step and one or more corrector steps. And the predictor step is a greedy step. So it wants to reach the solution as soon as possible. So it means that after a predictor step, we can have a certain amount of retirement from the neighborhood of the central path. So this is just an intuitive picture of a predictor corrector algorithm. And the aim of the corrector step is to get back into the neighborhood of the central path. So here we can see corrector step. And we want to define the predictor and the corrector search directions as well. And we gave somehow a general framework of how can we define the search directions in case of these predictor-corrector algorithms if we use this AET approach in the determination of search direction. So I mentioned that the predictor step is a greedy step, so it would correspond to the case when we go back to our Newton or scaled system, to the case when mu equals to 0 somehow. Just a second. So if we are looking here, then this would correspond to the case when we set mu to 0. But if we set here mu to 0, then we have to make a decomposition. So to try to decompose this a phi, this right-hand side, into two terms, and one which is depending on mu, and the other one which does not depend on mu, and for which fx of 0 is also 0. I should mention here that this decomposition is not trivial at all. So there are functions, for instance, that fourth function in the table, what I showed, for which this decomposition cannot be done in this manner, which means that in those cases, predictor-corrector algorithms in this manner cannot be given. Then if we have this decomposition, then if we set mu to 0, then we get the following for the predictor system. And from here we can determine, not from here, from the scaled system, we can determine the scaled predictor directions. In our case, when we deal with t minus square root of t, this corresponding gxs will be this minus x circle s. The corrector step would correspond to system 8, just with the corresponding right-hand side. So if phi is t minus square root of t, then we obtain this corrector system. And from here, we can calculate the corrector search direction by also using the scaling notations. Okay, so we determine from here dxc, dsc, the scaled directions, and after that, by using this quadratic representation, we obtain the corrector search directions. After that, we take the corrector step, and we define the so-called variance vector, but corresponding to this. So after taking the corrector step, we will get a VC with the corresponding WC and XCSC. And we will use this to determine the predictor search direction. So the scaled predictor system in our case, when phi t equals t minus square root of t, will be this with this right-hand side. And from here, by using the scaling notations, we get the predictor directions. And after that, we take a step. And in our case, the proximity measure will be this, where this is this Frobenius form. And we can see from here, from this 2v minus e, that we will need an extra assumption, name what I have already shown at the beginning of the algorithm when I started to speak about it, namely that this minimum eigenvalue of this should be larger than 1/4. So this is due to the specific search direction. So we have an accuracy parameter, we have an update parameter between 0 and 1, and we have a tau proximity parameter, and we assume that the interior point condition holds for the starting point, and that this proximity measure for this x0 s0 is less than or equal than this proximity parameter. We start to compute W, so this was the master of that scaling point of X and S by using this 6. After that, we determine the corrector directions by using those two systems and the scaling notations. After that, we take the corrector step. We compute the corresponding master of that scaling point of XC and SC because we will use them to get the predictor search directions. So after that, we calculate this delta P X and delta P S from these two systems, what I've already shown, and from the scaling notations. And we repeat this until this becomes less than an epsilon. So this is the sketch of the algorithm. So in our case, we have in a main iteration one corrector step. There are algorithms where we have we can have several corrector steps, but those algorithms where only one corrector step is used in each iteration are called Mizunov algorithms. And here we can see just the main steps of the complexity analysis of the predictor-corrector algorithm. So the first lemma is for proving the strict feasibility of the corrector step. So if this proximity measure is less than this, we can see that kappa this appears here. Then we can prove that this condition holds. What we should ensure during the whole process of the algorithm, and the full master of that step is also strictly feasible. The second lemma investigates the effect of the corrector step and the mu on the proximity measure. So we have an upper bound depending on kappa and its delta, but here the idea is that we could also prove that the smallest eigenvalue of this VC is larger than 1/2 in this case, and we obtained these upper bounds. After that, so we also dealt with the feasibility of the predictor step. So this lemma gives a condition for the strict feasibility of the predictor step, but we can see that we have here conditions. So these are the predictor step is strictly feasible if this value of this function is greater than 0, where this depends on theta, delta C, and kappa, and so on. But at the end, we make somehow a parameter fixing, and I will show immediately the final theorems. After that, so we consider this variance vector corresponding to the predictor step by using the corresponding WP and the quadratic representation as well. This lemma investigates the effect of the predictor step and the mu on the proximity measure. So here we gave an upper bound, but here we can see that this is also depending on this function u bar, what we had in our lemma related to the strict feasibility of the predictor step. And yes, and the other thing as well that we should prove during the whole process of the algorithm, this plus condition, what seems unusual related to other types of analysis. And the following, so lemma 9 gives an upper bound on the duality cap after a main iteration. So in this case, we obtain the following upper bound. What we did that we tried to prove that our algorithm is well defined for a set of parameters instead of fixed values. So usually when we have complexity analysis of these interior point algorithms, at the end there is there are given two values for theta and tau, for which the algorithm is well defined. There were some cases where the authors also proved that they are well defined for a set of parameters, and we tried to do this in this case as well. For this, we introduced this psi tau, where tau is that proximity parameter from the algorithm. And we proved that if we consider tau in this form where C bar is larger or equal than 2 and theta is between these two values, where G bar is greater or equal than 2, then if these two conditions are satisfied, then the algorithm is well defined. And in the final version, so if theta is between these two values and tau is given in this form, then the algorithm is well defined and it performs at most these numbers of iterations. We can see that we have this kappa in this complexity bound. And in the corollary, we can see this fact that we prove that the predictor corrector algorithm is well defined for a set of parameters instead of fixed values of parameters tau and theta. And so what are the concluding remarks? So we introduced a new predictor corrector algorithm for solving this horizontal linear complementarity problems over Cartesian product of symmetric cones. So this was an extension of our previous result that was only for P star kappa LCPs. And I mentioned about possible further research. So I mentioned that it would be very interesting to define whole classes of AET functions for which we can define algorithms and for which we can also prove and to achieve this complexity bound, so this polynomiality, of course, in kappa and size of problem and in the rank of in this case. But and it would be also interesting somehow to compare them also to the corresponding kernel functions as well. And it would be also interesting to extend results to non-symmetric cone optimization problems and to generalize these results related to this more general framework by considering this Cartesian product space to non-linear complementarity problems over symmetric cones. So and just to for the end, I just wanted to show that why it's important and interesting to use this unified approach. So if we consider these three symmetric cones, what I have already shown in this presentation, and if we take the exponential and power cone, then Anderson, establisher of MODEC, mentioned that almost all convex optimization problems appearing in practice can be formulated using these 5 cones. Okay, and here is the list of references, and thank you for your attention, and thank you for Professor Sándor Németh, who invited me